Now in this lesson, we're going to be talking about the cosine rule. Now in a previous lesson, we already talked about the sine rule that allows us to perform something similar to SOHCAHTOA on a non-right angled triangle. And now we turn our attention to this cosine rule that allows us to extend Pythagoras' theorem to non-right angled triangles. Now, to introduce the cosine rule properly, let's start with a picture of some random non-right triangle. Now the key insight that you need to have for the cosine rule is that you can always take any non-right angled triangle and break it up into two right angled triangles. Now that we've split this triangle in half, we can go ahead and mark on all of its side on both of these diagrams. Now for the cosine rule, the proof can be a little bit intimidating the first time you see it, despite the fact that it's actually pretty straightforward. So to show you this, I'm going to do a specific case first, and then we can do the more general case right afterwards. Now suppose you had this triangle over here. Suppose you knew that one of the sides was 6, one of the sides was 5 units, and the angle between them was 60 degrees. And for argument's sake, you didn't know what this length x was equal to, and you wanted to find it. As we said, you'd start by actually splitting the triangle into two parts. So let's go ahead and do that. Now this original triangle had no right angles in it, but both of these two triangles are right angled triangles. Now we're going to need a game plan to find this side x over here. Now the first step is going to be to find the length of this side over here. After that, we're going to want to find the height of this triangle since it's the same as the height of the other triangle. After this, we're going to want to find the base of this triangle. And then finally, we can go for our goal, which is to find x. Now to begin with, it's actually pretty easy to find the base of this triangle over here. You just have to take the cos of 60 and multiply it by 6 because this triangle is 6 times the size of the unit triangle. Now if you don't like doing that, you can also just use the cosine of theta. You can just say that this bottom side over here is the missing side and you can solve for it. If you multiply both sides by 6, you just find that m is just 6 cos 60, as we said before. Now if you check on our special ratios, you'll find that cos 60 is just 1/2, so 6 cos 60 is just the number 3. So let's go ahead and rub out all of this information and just keep the number 3 at the bottom. Now in the next step, we said that we wanted to find this height h, and we can do this with the Pythagoras theorem on this triangle over here. Now if h squared plus 3 squared equals 6 squared, we know that 3 squared is 9 and 6 squared is 36. Now 36 minus 9 is just 27, and finally 27 is just 3 times 9, so that means h is just 3 root 3. Now for this third side, we know that the whole length is 5 and this length over here is 3. So we can just go ahead and subtract 3 from 5. Now that we know the length of this bottom side, we can just go ahead and perform Pythagoras' theorem on this triangle over here. Now we know that h is 3 root 3, and that means that h squared is just 27. Also, 2 squared is 4. Now 4 plus 27 is just 31, and that means x is just the square root of 31. We assume lengths can't be negative, so I don't include a plus minus here. Now as you can see, we've done something that we'd usually use the Pythagoras theorem for on a right angled triangle. We have two sides and an angle which we've used to find a missing side. And now I think we're ready to repeat these steps on these more general triangles over here. Now in order, we first found this side down here, then we found the height, then we found this side, and then we used that information to find this c over here. Now let's first turn our attention to this side over here. We know it's just going to be a times the cos of c, so let's just write that. Now since we know that this side over here was originally b, and we cut away a cos c of it, then we know that this side over here is just going to be b minus a cos c. Now the second step was to actually find this height h here, so let me label it. Now just like we did last time, we want to write Pythagoras on these two triangles over here. But this time we're going to be a little bit more clever. I want you to realize that h squared is just a squared minus the bottom over here, and it's also the same thing as c squared minus the bottom over here. Now, whilst these are the exact same steps we took last time, all of these extra symbols make things look a little bit complicated. But the first thing we notice is that this h squared doesn't actually play any role in this equation, so I've just faded it away a little bit. Now I claim that this equation over here is the cosine rule, but it's not in a very familiar or recognizable form. So we're going to go ahead and simplify it a little bit to put it in one of those forms. Now, the first thing we're going to want to do is expand this quadratic over here. Now, I don't want you to be intimidated by this. To expand a perfect square, remember, we just square the first term, then square the last term, then we just multiply both terms by each other and the number 2. Now I'm going to go ahead and expand this minus sign into these 3 terms. So you'll get minus b squared, and then a plus here, and then a minus here. And now we just notice that this term over here and this term just cross each other out. If we just go ahead and take both of these 2 terms and move them to the left-hand side, we'll have the final form of the cosine rule. Now I also want you to note that I swapped the left and right-hand side when I wrote this. Now when you see this formula in this form for the first time, I really hope that it looks somewhat familiar to you. Notice that we just have c squared equals a squared plus b squared. That's just Pythagoras' formula, but then we have this little part over here just tacked on. If we were to redraw this triangle over here, for the case where it's 90 degrees, then I hope you'll remember that the cosine of 90 degrees is just 0. You should check this with your calculator or a unit circle, whichever you prefer. Now in this case where we do have a 90-degree angle, you'll notice that this term over here just crosses off, and that leaves you with c squared equals a squared plus b squared, which is the ordinary Pythagoras theorem. In the case where there are no right angles in your triangle, you will actually have to use this formula over here. Now since it has a cosine of c in it, you can actually use it to solve for the angle as well. So let me go ahead and give you an example of how you might use it. Now suppose you're in a situation where you had a triangle, like this one over here. You knew the side lengths, but you didn't know the angle. To solve for the angle, let's start by actually just writing out the cosine rule, and then labeling the sides and angles with their corresponding letter. We then go ahead and directly substitute in these values. Now we can go ahead and perform all of these multiplications. 4 squared 16, 2 squared 4, 3 squared 9, and 2 times 2 times 3 is just 12. Now we can just move these 2 terms to the left, and then we can say that 16 minus 4 minus 9 is just 3. And then by dividing this minus 12, we notice that the cosine of c is just minus 3 on 12. Now we take the arc cos of both sides to get rid of the cosine. Now remember, arc cos is the inverse of cos, so we can cross arc cos and cos out. Now we can just go ahead and find the value of c with a calculator. I'll do so in degrees. So in this case we notice that our missing angle is just 104 degrees. And this just shows you that the cosine rule is very useful to find missing angles and sides. Now just like the sine rule, the cosine rule also has some special cases. I'll go ahead and discuss them on a new page. Let's imagine that you started off with another triangle. Now if you're in the situation where you have the length of 2 sides and 1 angle, but you don't have the length of this side that's touching the angle, again, you'll find that there is actually more than one possible length for this side B. To show you this, I'll draw the exact same mechanism I drew for the sine rule. Now again, you've got a plank that's fixed to a wall over here, and it's attached by some rotating hinge. If you fix the length of this plank, it turns out that there are going to be 2 places where it hits this bottom line. So as you can see, because B has 2 possible lengths, when you actually try to solve for B, you're going to find that there are 2 possible answers. And this is the ambiguous case of the cosine rule. So as we said, if you're using the cosine rule to solve for a missing side that's touching a given angle, you'll find that it's possible to have more than one correct answer. And with this, we've actually completed our discussion on the cosine rule.